To make a buffer solution, I will typically start with a solution of just acid. And then I will add sodium hydroxide to that solution so that I turn my acid into conjugate base. And when I get to the ratio of conjugate acid and conjugate base, that gives me the pH that I want for my buffer, then I will stop adding OH minus. So I might add enough OH minus to get to this pH, and then I stop, and then I have a buffer at that pH. Notice that every acid that was there originally is either an acid or a conjugate base. And so the total number of acid molecules that I have to start with doesn't change. Their character changes. They either stay as the conjugate acid or they get changed into the conjugate base by removing a proton. And so the total amount, the total concentration of acid that I started with is just simply split up into the amount of conjugate base plus the amount of acid that I have at any point, at any pH point on my titration curve. This total amount of acid that I started with is called the analytical concentration of the acid. So it's equal to the concentration of the acid form and the conjugate base form in the solution at whatever pH my buffer is buffered at. If we think about the expression for our acid ionization equilibrium constant, which is the conjugate base concentration times the H3O plus concentration divided by the conjugate acid concentration, we can rearrange this to Ka divided by H3O plus concentration is equal to the conjugate base concentration divided by the conjugate acid concentration. And so we can find the ratio of conjugate base to conjugate acid in our solution if we can measure the pH and therefore know the concentration of H3O plus, and we know what acid we're using, so we know the Ka. So this ratio will tell us the ratio of A minus to HA in our solution at any given pH. If we know the total amount of HA that we started with, then we know that A minus and HA have to add up to that total amount. And so this equation plus this equation will always allow us to calculate the concentration of A minus and the concentration of HA, two variables, two equations, in any solution given the pH, the Ka, and the total analytical concentration of acid that I started with. The concentration of conjugate base and the concentration of the conjugate acid in my buffer solution is important for the following reason. When I no longer have enough conjugate base or enough conjugate acid in solution to soak up extra strong acid or extra strong base that I add to my buffer will no longer work. And so we say that the buffer is broken. So if we look at this titration curve, we can see that the addition of strong base for about 20 milliliters resists changes in pH. But once I get close to this equivalence point, I start to see a rapid rise in pH, and this solution is no longer resisting changes in pH. So this is no longer acting as a buffer. There is a point at which I've added enough OH minus that I've used up all my HA, and I no longer have a buffer because I don't have enough HA in solution to soak up the extra OH minus that I've added. I could do the same thing if I continued to add strong acid. At some point, I would use up all my A minus and I would see a big decrease in pH as the extra strong acid that I add had nothing to react with and all became a change in pH of the solution. So a buffer will only work when I have appreciable amounts of A minus and HA. In fact, the strength of the buffer towards acid addition is the concentration of A minus that I have in solution, because I can add strong acid until I use all of that up, and then the buffer no longer works. The buffer strength towards addition of strong base is equal to the amount of HA that I have in my solution, because I can add OH minus up until the point that I use all of the HA up, and then my buffer will no longer work. So buffer strength has to do with the amount of A minus and the amount of HA in my solution, which I can find from combining these two equations.